All right. So let's review this for just a second. Now, I left you on your own last time to do RA and AC, right? Yes? Are those the two we didn't do? So let's look at RA. Okay? And let's do RA together.
Yay.
All right, so if I ask you to do the electron configuration for RA, what would it be? Did you do it?
What's the gas?
All right, let's do the complete one, and then let's do the using the noble gas.
The gas?
Well, you got to get practice doing the complete one.
Okay.
Okay.
Well,
All right.
how often will it ask
So where are we going to start with RA?
for? 1S.
1S,
2.
2. Then comes,
2S. 2.
then comes,
2P. 6.
then comes,
3S. 2.
then comes,
3P. 6.
then comes,
4S. 2.
then comes.
3D. 10.
Like it. Then comes.
4P. 6.
I like it. Then.
5S. 2.
And then.
4D. 10.
I like it. Then.
5P. 6.
I like it.
6S. 2.
All right.
Now we got 4F.
Nice.
4F. 14.
14.
Oh, yeah.
Excellent. Okay.
Why did we not
Oh
do
yeah.
short?
4F. 14.
All right. Then we go
5D. 10.
5D10. I like it.
6P. 6.
I like it.
And then 7S2. No, 7S.
No.
Yeah, 7S2.
7S2.
7.
Okay. So if we had to do it the long way, that is what it would be. All right. But does everybody see how to do it the long way in case they ask you to do that on the AP exam? And all we did was follow the what? Periodic table. That's all you got to do. Is just follow your periodic table. Right? We remember this? Because we're going to have a quiz on this tomorrow, and we can do it.
No, we
Yes, we can. We can definitely do it. Okay? All right. Now, do we like writing it out like that? No. Let's do it using the noble gas configuration. What's the noble gas that occurs before RA?
RN.
RN, right
Yes.
there. So I would put RN in brackets and then 7S2. So much shorter. Okay? And so much easier. Do we see that? Normally on the AP exam they don't care. So on your quiz tomorrow I'll probably tell you like you can use either one, except on one of them I'll probably ask you to give me complete, just to make sure you can do it.
No, come on.
Come on now. Okay?
That's like
All right.
what the thing is for like healing or something.
Yes, ma'am.
Are we gonna be doing like the S and the M and the,
Yes.
like, all these other-
Yes, and that'll be on the test too.
On the little L one, can it, like, you always do the N minus 1 to get that one right? Not always?
No.
You just look at the letter?
You just look at the letter. All right. So, let's talk about this. Okay. All right, so let's say we had to do the orbital notation for RA. So, I'm just going to put RN in brackets, and then what do I have to draw?
2 little, or just 1 little.
7S. So, we're going to go
Up.
up and then down.
Why couldn't you just say 7S2? It's not like there's another 7S2 on the periodic table. I don't even see why you have to do this.
All right. So now, let's do the quantum numbers for the last one that we drew, because that's what you're going to do tomorrow. You're going to do the set of quantum numbers for the last arrow that you drew. What's my N for this?
7.
7. Okay. What is my L for this?
Zeros.
0. What is my M for this?
0.
0. And what is my S for this?
Negative.
-1/2. So let's talk about where we got those numbers from. Where did I get N from?
Is your
Right there.
energy level.
My energy level. Where did I get my L from? The S. Okay, so that's where I got N. This is where I got L. If it's an S, what's L?
0.
If it's a P, what's L?
1.
If it's a D, what's L?
2.
If it's an F, what's L?
3.
Okay, cool.
Okay? where did I get my M from?
Your N is.
I don't know.
I don't
Hold
know.
on, time
Okay.
out.
So
That's
we
the thing, mine
we
is
go to the middle one, and we always assign the middle one what? 0. So for an s orbital, M can only be what? 0, because there's only one. Whereas, let's pretend we had a p right quick. This is hypothetical, okay? I would assign the middle one what?
0.
Then this one would be,
-1.
and this one would be positive 1. Do we see that? So if the arrow was here, M would be -1. If it was here, M would be 0. And if it was here, M would be positive 1.
Oh, so you
Okay.
just put a 0 in the middle?
Just put a 0 in the middle and then go out like a number line. Okay? And then where do I get S from?
That's if it's
The
there.
arrow.
The arrow. If it's a up arrow, we say it is a
Positive.
positive S. If it's a down arrow, we say it is a
Negative.
-1/2. We see this? We feel good about this? We should feel good about this. Okay? I'm hoping that we feel good about this. Okay? Now, I've already told everybody, next year, I really think I'm going to,
You could
write my
just show
own
your-
set of notes,
You
because
could just show your class the videos.
I've skipped around so much. Yeah, next year I should. All right. So keep in mind, because I don't want everybody to think that, like, okay, so 2p is not in the same energy level as 2s. It technically is when we talk about energy levels, okay? So here's energy level 1. It only has a s orbital, right? Here's energy level 2. It has a 2s and a 2p, okay? Which one's lower in energy? 2s, okay? And energy level 3, I've got a 3s, a 3p, and a 3d, okay? 3s is lower in energy than 3p than 3d, but who fills before I fill in 3d? 4s. Do we see that? Because 4s is technically lower in energy, but it doesn't mean that 4s is in the third energy level. Does that make sense? Okay? So don't keep in mind the S, the P, and the D are still in the same energy level. 4s just happens to be lower in energy. So it fills first. I know.
So all the
It's
S's
just
are
a
lower
charge.
in energy.
It's
than
Yes.
the
first.
Okay.
Like, for-
So my whole point in that is, don't get confused. If they ask you how many electrons total can you fit in the third energy level, I'm going to say, well, I can put 2 in S, 6 in P, 10 in D. So total, I could fit 18 electrons. Okay? Because in the third energy level, I have an S, a P, and a D. All right? But you know the order they fill in just by looking at the what? Periodic table. Right? So don't forget that. So, you good? We're good. Now, this section of your notes on the next page, I think it's page 17 maybe? 15? Okay. On the next page of your notes, this is where they wanted you to write the quantum numbers for the last electron that you drew. But we already did that, so I'm writing my own thing in here. Okay. So this is just Snellick notes at this point. Alright. So we're going to talk about oxidation numbers using orbital notation and electron configuration. Okay. Now, what are oxidation numbers? For instance, okay, if I gave you CO2 and I asked you for the oxidation state of oxygen and carbon in this, okay, what do I know the oxidation state of oxygen is normally when it bonds? -2. Thank you. So what would my oxidation state of carbon be here?
Positive 4.
+4. Because I have 2 oxygens, so -2 times 2 would give me a -4. So since this is a neutral molecule, my carbon has to be what? +4. Do we see that?
I do.
Everybody see it? You got it? Okay. Well, we know that because I made you learn oxidation numbers last year. Remember? We did this for a while. Okay. I made you learn. No. Olivia says no, we did not. All right. I made you learn oxidation states. But how could I know that if I didn't memorize it? Okay. Why is it, okay, or maybe the thing is, maybe a better explanation is, why is it that oxygen forms a -2 oxidation state when it bonds? Okay. Well,
I don't know, but I think you're about to tell us.
you're right. You don't know, and I am about to tell you, okay? Well, let's write, what's the electron configuration for oxygen? Okay, so we start with 1s2. I'll talk to myself, all right. Then next comes 2s.
2.
And then next comes 2p, 1, 2, 3,
4.
4. We all agree with that? Okay. So if I drew this out, 1s2, 2s2, 2p, 1, 2, 3, 4. Why is it oxygen normally forms a -2 oxidation state when it bonds? Okay? Because what does it do?
Leaves out 2.
It fills in those empty spots in the orbital. Do we see that? So that's why when it bonds, oxygen normally forms a
Is that everyone? Is like that?
Huh?
Is everyone up there like that?
What do you mean?
Like every.
Like if you were to do this, could you?
Yeah,
do the
if
same
I were to
thing?
do
Yes. Yes.
Is it basically because of the lone
Huh?
pair? Is it
That's
one
cool.
lone pair?
It's just saying it's got 2 empty spots in its orbitals where it can accept electrons. And remember, when we form bonds, like in this case it's a covalent bond, it's because we're doing what? We're sharing electrons. So there's 2 spots where oxygen can let carbon come in and share electrons with it. Okay? So that's why oxygen normally forms a -2.
But hydrogen, it's a 1s1, so.
Because it normally gives it away. Okay? I'm going way off track to answer that question, so if you don't get this, just ignore it. Okay? Because I'm about to jump off to do this. And we did this last year, but you're probably not going to remember it. Hope we'll just ignore this if it makes you crazy. Okay? All right, so you're talking about, because hydrogen normally forms a +1, right? So like we've got our CH4. That's because, okay, carbon comes in, and carbon's 1s2, 2s2, 2p2. Okay, so if I draw that out, that's 1s, 2s, and then 2p, 1, 2. So what carbon does is it takes this electron right here, and instead of it being a down arrow, it pulls it up here. And it takes its s and its p orbital, and it combines it. Okay? So
Is
hydrogen...
that just more energy efficient?
Yes, it's just more energy efficient because remember, we have electrons are the same charge. So we would call this right here electron-electron repulsion. Okay, they're pushing against each other, so it works better for me to just take this one and dump it up here. Now they're not repulsing because there's only one in each one. Okay, so hydrogen comes along and it's got its 1 electron, so it says, okay, then I'll share here, 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 and here. I'll give them to you because I've only got 1.
Okay.
So that's why your hydrogen is normally...
So the donator is going to be positive?
Your +1. Hydrogen came in and donated 1, 2, 3, 4. There's 4 of them, +4. Carbon there is a -4 because it accepted 1, 2, 3, 4 to make the bond.
Okay, that's easy.
We see it?
We see it.
Remember, we talked about these are what we call hybrid orbitals. So now instead of having an s orbital and a p orbital, I would say this is an sp3 orbital. Because I've got 1 s and 1, 2, 3 p's. So it's no longer a 2s and a 2p orbital, it's an sp3 orbital.
We just got into college knowledge.
There you go, college knowledge. I like it. We just did college knowledge.
Is it ever gonna ask us a question like that on the test? Like,
I don't think hybridization is in. Ooh, when we get to bonding, it may actually. I was just kidding. Yeah, we're gonna get to that. I don't know. I was about to tell you no, you weren't gonna have to know it, and then I realized I was just kidding. You are, but you did it last year. I promise we did it.
We did knowledge.
We did it, knowledge. So this year, once we do it, it's just going to be a repeat, and our brains are just going to wake up and come alive and be like, yes, we know this, and we get all excited inside. It's great.
Yeah, we will.
I don't know. Libby's not feeling it.
Okay, well, Olivia didn't have me last year, so sorry, Livy. All right, but does everybody see how oxygen normally forms a -2 then? Because it's got 2 empty spots where it can accept an electron with somebody else. We see that? We see that? All right. So what if I asked you for the electron configuration of O2 negative? Woo, we just got fancy. Okay? Now, we know this is the electron configuration for a normal oxygen atom, right? If it became 2 negative, what does that mean that I did?
You added 2.
I added 2 electrons. So my new configuration would be 1s2, 2s2, 2p,
Let's see.
6, because I added 2 electrons. Do we see that?
Oh,
I'm on it today.
You are on it today. I like it.
okay.
We see that?
Yes.
Because sometimes on the AP exam, I'm not going to guarantee you that they're just going to give you fluorine and say, what's the electron configuration? I am pretty confident that they may do something like, well, what about F negative? And you say, well, I would do the normal electron configuration for fluorine and then say, since it's negative, that means I did what?
Added.
Added 1 electron, so just add another electron in there.
If you make it more positive, you take 1 away.
Yes. So if it becomes positive, that was my next example.
Deb is
You
on
be
the
good
ball
there.
today.
Deb, you want to teach today? I mean,
Hey, blind
I feel like
I think after he taught your pre-AP class.
I don't know. Maybe it's like, I know I did so bad on the ACT that I'm not trying to make up for it.
no. All right, so let's talk about sodium. Okay, because sodium is a common example. All right. So sodium's electron configuration is 1s2. What comes next? Help me out, people.
Wait, what?
Sodium. I'm talking about
It's
sodium.
1s2, 2s2, 2p6, and 3s1.
3s1. There we go. Okay. Now, what's the most common oxidation state that sodium forms? Na positive, because it's in column 1, and everything in column 1 goes what?
Positive.
Positive. So, what if they asked me for the electron configuration of Na positive? Since it became positive 1, I know I did what?
Took 1 away.
Got rid of an electron. Which electron did I obviously lose? 3s. So since I lost this 1, that whole 3s orbital goes away. So my new would be 1s2, 2s2, 2p6. We see this? Huh?
Just like math.
You're feeling it? I'm feeling it. I feel like we just did really good and I'm excited.
Elmwood County's feeling it.
All right. As we eat our Munchos potato crisp.
They are delicious. Have you tried
Munch
them?
over for the monkeys.
All right, how we feel about this? Good?
Yeah.
We feel like we're going to like ace this quiz tomorrow and make a 100,
If you make it like this and not add some weird.
at least an
number.
80. Okay. At least we're shooting for a B. All right. At least an 80.
And then you'll be even like,
Yeah, if we all make hundreds and you expect.
Put expectations low and then I'll be really excited when you do well. Okay.
What
All
happens
right.
if we all made 100?
So we're all going to make an 80 tomorrow? Okay. All
I'm
right.
making 100.
What
Nice,
would we
I
get
like
if
it.
we all made 100?
If you all made
Let's
100,
have a pizza party.
100 in the.
the joy and satisfaction that you all made 100.
You get some CO2.
All right.
But we should have lunch in here on next
We
Thursday.
fill the room.
Let's
with
continue. All right, so we've accepted long time ago when we started doing electron configuration that sublevels have different energies, right? We know that 2p is a higher energy level than 2s, right? All right, we're all in agreement of that? Okay, and we know that by going on the periodic table. We even know the order of energies, right? I can go all the way across the periodic table from beginning to end and write the order of energies, can I not? Which energy level has the lowest energy on the periodic table? S, right? So S would be the lowest. What would be the next lowest? P. What would be the next lowest?
D.
And then the one with the highest energy level would be F.
What is
Feel
G?
that? We know that. G would be what we're going to have to do if we keep adding elements to the periodic table.
Okay. Let's not do
Okay.
it.
Because the periodic table is filled in now. So I guess next we would start a
Start a separate little box.
8S. I don't know.
You shouldn't have to make it.
Yeah.
We have to add up, like, maybe extend it out.
I mean, we're going to have to come down here because, you know, that's what comes next because we've already filled in 118, so next comes.
Hey, you can just leave the
I
guys
think
down.
we
take
found
them.
it all. I really think we found it all.
You think we found it all?
Now, does
They're
that,
not gonna ask us about those extra ones on the AP exam. are they?
No, 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 no.
Good.
now
They're
does,
not.
does the UUO or whatever, does that count as a noble gas? Does that
yeah.
like,
No.
put us in the same
No.
It counts?
Yeah.
Alright. Got it.
All right. So now we've got to be able to explain all of this on the AP test. All right, and I'm going to give you a lot of stuff to work with on explaining today. So I need you to hold tight with me on explaining. Okay. So the first thing we all know, electrons repel each other because electrons are what?
Negative.
Negative, and like charges repel. Opposite charges attract. That would be the second thing. Electrons are negative, so they are attracted by the positive nucleus. This is stuff we should already know, so we're comfortable with this. This is nothing new. All right. And then the last thing we know is that forces, no matter if they are attractive or repulsive, dissipate with increasing distance. What does the word dissipate mean? Go away, okay, or decrease with increasing distance. And the equation we use for that is Coulomb's force, which is F of C, is equal to Q1 times Q2 divided by R squared, where Q's are my charges and R is my distance. Okay? So, let's say hypothetically that I have a positive charge and a negative charge. So is this going to be an attractive force or a repulsive force? An attractive force, right? So as my distance goes up, this number in my denominator is going to get what? Bigger. So what's going to happen to my attractive force? It's going to go down. Do we see that? Okay. Now let's say maybe that both of these are negative. So now do I have an attractive force or a repulsive force? Repulsive. And as the distance between those two objects increases, what happens to this repulsive force? It goes down. We see that? Okay. They like this equation on the AP exam to talk about attractive and repulsive forces. Okay. There is a question on the practice sheet that you're going to do Thursday that asks you to explain something using this equation. It gives you the equation and says, okay, so explain what's happening using this equation. Okay? What you need to remember is all I'm looking at is how distance is affecting force. Okay? Don't worry about your charges. Okay? Don't worry about them. Just know if it's a negative and a positive, I'm dealing with an attractive force. Whereas if it's two negatives or two positives, I'm dealing with a repulsive force. Got that? You're with me? Of course you are. I like it. Okay, so let's talk about something called radial possibilities. Okay? Radial, not possibilities, probabilities. Okay? Radial probabilities. Okay? Radial probabilities is just the chance of... It's got to be an announcement. It's not time for the bell.
Please consideration. William Harlow and Tanner Neely come to the high school office. William Harlow and Tanner Neely come to the high school office.
All right. So, radial probabilities. We're talking about the chance that an electron has to get close to the nucleus. Okay? Or you can see it here. The electron gets zapped by the nucleus. Now that's in quotation marks because please do not write on the AP exam. The electron got zapped by the nucleus. Okay, that's not exactly our chemistry terms that we want to use there.
We get it wrong.
Okay. I don't know. I think it depends on your grader on whether they would count it wrong. Just don't write zapped. Okay.
What about penetrates?
They might think it was
Okay.
cute.
They'll take that.
Okay, good.
Okay. All right. So, what we're talking about is the chance that the electron gets close to the nucleus. So we would say the chance that it penetrates the nucleus. That is the exact word that they use. Okay. So it gets closest to the nucleus. Now, who has a better chance of getting close to the nucleus, an s orbital or a p orbital?
Yes,
S. Why?
because it has lower energy.
Because it has lower energy. and it's closer. I like that. Okay?
It penetrates.
All right, so because it is lower energy, okay? Relate these questions,
So important.
excuse me, relate these answers to lower in energy as much as you can. Use energy in your explanations, they like it. Okay? If you use energy in your explanations, then people really like it. Okay? The 2s electron is more attracted to the nucleus than the 2p, which makes the 2s electron lower in energy. Okay? How do we know that the s orbital is lower in energy? Because if we look at a radial probabilities graph, do you see this? 2s stands a better chance of getting close to the nucleus. Okay? That means 2s is lower in energy. Do we see that? And if you think about this example down here, and you cannot use this, okay, but it does help you. You can't write this on an AP exam, but it does help you understand it. Think about a hyperactive child, okay? You know those kids that just have an endless amount of energy? They'll about drive you insane, okay? The best chance for making that hyperactive child be still and be quiet is to put them as close to their mother as possible, okay? All right, is to put them as close to the mother as you possibly can, okay? The further away they get from mama, the crazier they act, okay? The energy level goes up. It's the same thing with electrons, okay? Think of the nucleus as the mama, okay? The closer those electrons are to the nucleus, the lower they are in energy. Whereas the farther out away from the nucleus they get, the higher in energy they get. Okay? Make sense? Make sense? Okay. Food will keep them calm for a moment, but then it makes them crazy.
I don't know, it's something else to do.
I was
crazy near my
I don't know, a firm smash doesn't.
All right, so moral of the story here. Here's what you need to get from all of this, okay? The greater the penetration, the less energy that an orbital has, okay? That's how they came up with the energy orbitals, okay? Is they looked at the electrons and say, okay, how often do the 2s electrons get pulled in close to the nucleus? How often do the 2p electrons get pulled into the nucleus? It happens more with 2s than it does in 2p, so 2s is a lower energy than 2p.
Oh, is that how they measured it?
Okay? Yeah. That's how they decided the energy levels, was using that. So, we already know S has a lower energy level than P, which has a lower energy level than D, which has a lower energy level than F. So, S's penetrate the most, and F's penetrate the least. And what are we talking about penetrating?
Nucleus.
The nucleus. Thank you. You are on it today.
Just reading the board.
Does help. Now, sometimes our energy shells overlay, okay? Especially our D's and our F's and our S's, because if you notice when we start getting in these transition metals, what is all together here? My D's, my F, and my S's, right? So a lot of times our energy levels will overlay. So what this causes is this causes some exceptions.
Great.
Okay. This causes some exceptions to the rule. All right. So, what are these exceptions? Okay. Let's talk about this down here. Okay. Now, on the AP exam, they are not going to ask you, they're not going to give you one of the exceptions to the rule and ask you to give the electron configuration for it and expect you to know the exception. Okay? What they would do is give you the exception themselves and then ask you to explain why. Does that make sense? Okay? So, let's look at something like chromium. Okay? So, why is it? Normally we would say chromium is 4s2, because that happens right here. And then 3d, 1, 2, 3, 4, right? Does that make sense? That's what we would say. But if we look at chromium and we look at its electrons configuration, it is not this. It is 4s1, 3d, 5. And we say, but why? Why would that happen? If you get stuck on an electron configuration problem and you can't figure out the answer, you need to draw it. Okay? So if I drew this out the way I thought it should be, That's the way it would look. And then if I drew this out the way it really is,
Oh, it's just because it's gonna make it easier. That's not it. Does that do
That's
that
the way
for
it really
all of them, or
is.
is that just a few?
we'll look at that in just a second and you'll see. So, when we look at it like this, what do we notice? Okay? Why would I want to take this electron and move it here instead of keeping it paired in the 4s?
More energy efficient.
It's more energy efficient. Why is it more energy efficient?
Those two are repulsing against each other.
Excellent, because this right here is what we call electron-electron repulsion. Remember, electrons are negative. Do they want to be paired together? No. That's why when we fill in the orbitals, we always fill them in going up before we come back and pair them, because they don't like being paired. So, if this 4s electron jumps up to the 3d energy level, now I have minimized my electron-electron repulsion. So now what have I done to my energy?
Lowered.
I've lowered my energy, which makes the atom more stable. Do we see that? Yes. That's why when we just did that CH4 earlier, when we did that hybrid orbital, that's why carbon, which is 1s, 2s, 2p, when it bonds, it always takes this one and pulls it up.
So if there's an extra one to fill, it's going to do it. There's no exception on that.
And not all, and you wouldn't have to draw that exception. They wouldn't ask you to draw it. They would just ask you to explain it. Why does it do
What
this?
could your drawing be an explanation?
I would draw. I mean, you can draw it and show this, but you would need to say it minimizes the electron-electron repulsion, which
Well,
lowers
like
the
what you got
energy.
up there is
Yes. Yeah, this is an explanation.
Why-
I would just take those and put them in complete sentences. They, for some reason, are just more favorable if you write it out completely.
liberals.
Exactly. Yes, sir.
Why didn't you put a down arrow for it?
Because this is what we would normally expect it to be right here. So this is what we expect, but this is what it is in reality. Okay? Why? Because these electrons don't want to be paired because they're repelling each other because they're both negative. So if this one jumps up, then it minimizes the repulsion, so it allows the atom to be at a lower energy level, which is what we want. We want to be as low as possible. Make sense? You're with me? I haven't lost anybody? All right. To go back up here, I just wanted to get the exception out of the way. Don't forget the names of your groups. So in case on the periodic table they talk about alkali metals, you're not staring at your periodic table going, I don't remember where the alkali metals are. Okay? Column 1 is your alkali metals. They're the most reactive because they're trying to get rid of that electron. Group 2 are your alkaline earth metals. Okay? Group 6A or 16, these are your chalcogens. Okay. They form all your metal oxides, like your iron oxide and your zinc oxide. 17 or group 7A are your halogens. That's where we get all our salts from, or most of our salts. And then, of course, group 18 or 8A, depending on what periodic table you're looking at, those are your noble gases, okay, which are the least reactive on the periodic table. Can they react, though? Yes. Don't ever write they are a noble gas, they cannot react. Okay, they can, they just don't very often. Okay? All right, you with me?
Yes.
I feel like we're feeling good. So let's move on to periodic trends. Yay. We won't talk about the trends a lot today. We're going to talk about how we're going to explain the trends, okay? And then tomorrow we'll knock out all of the trends, because once you get down how to defend them, it's easy, okay? There are only 2 explanations you need for periodic trends. Just know that a trend is not an explanation, okay? What do I mean by that? The first trend we're going to talk about is the size of the radius, or the size of an atom. Okay, I know as I go across the periodic table, my radius decreases. Okay, I know as I go down the periodic table that my radius increases. So if they ask me, why is it that fluorine is smaller than nitrogen? I cannot say, because as you go across the periodic table, the size of the radius decreases, therefore fluorine is smaller than nitrogen. No. No. And they're not even going to give you a half a point. Okay? They're going to read it, say, oh, they memorized a trend and they cannot explain why. That's exactly what they're going to say, which means they don't know anything. Okay? So a trend, please remember this, is not an explanation, ever. Yes, ma'am?
It's kind of like when, like in the last one, you were talking about how many oxygens, like there's more oxygens, it's more like, there's more, remember? we were talking
Yes.
about, the electromagnetic
Yes.
radiation and stuff.
Right. You got to be able to explain. And so we're going to talk about, there are really only two arguments you need. Okay? So let's talk about them. The first one we can explain using effective nuclear charge, or the symbol for that is ZEFF. We will always use this argument if we're talking about going across the periodic table. Okay? So if you're asked to explain the difference between two things that are in the same period, now remember periods go what? Across. Okay? Families or groups go up and down. Okay? So if you're asked to explain something, a trend going across the period, you're always going to use the effective nuclear charge, okay? Or the ZEFF. That's the symbol for it, ZEFF. All right? So how do I know what ZEFF is? ZEFF is equal to whatever the group number is. Okay? So if we look at this here. Okay, so group 1, the effective nuclear charge is 1. Group 2, the effective nuclear charge is 2. We skip the transition metals when we talk about ZEFF. Okay? They won't ask you to explain those. There are so many exceptions in there, it's not even funny, so they don't expect you to know that at this level of chemistry. Okay? So, the effective nuclear charge is 3, then 4, 5, 6, 7, 8, but they normally won't ask you to explain this column. Normally they'll stop right here. Okay? So do we all see how to get the effective nuclear charge? If it's in group 1, it is, and 2, and 3 or 13, depending on which periodic table you're looking at. 3, 4, 5, 6, 7. We're good? That's not hard, is it? Not hard at all. Okay. So we get the ZEFF from whatever group it is. The higher the ZEFF, or the effective nuclear charge, okay, the more positive the nucleus, so the more attractive force there is coming from the nucleus, so it draws the electrons in or it holds them in place. And you need to relate this to energy whenever you possibly can. Okay? So those electrons would have a lower energy. But what would happen to the amount of energy it would take to take one of those electrons away? It would be a lot higher, right? So you're going to be able, and we're going to have a lot of trends, you need to be able to use energy to explain all of these trends. And you'll see that when we get to them, how we relate it to energy, I promise. It's not difficult. So do we all understand what effective nuclear charge is? Okay? As I go across the periodic table, what happens to my effective nuclear charge? It increases, which means the nucleus becomes more positive. Okay, which means the electrons become more attracted to the nucleus. You need to know those three things, so we're going to say it one more time. As I go across the periodic table, my effective nuclear charge increases, which means my nucleus becomes more positive, which means my electrons become more attracted to my nucleus. Can you explain that?
Can you just say they have a lower energy with that, or would you just...
No, you need to say all three of those things.
No, I'm saying
So that's
them being attracted to the nucleus, you have to say they're attracted to the nucleus.
I would say they're more attracted to the nucleus because the
So
nucleus
that
is
would be
more
the
positive.
explanation.
That would be the explanation using ZEFF. Okay? And then you'll see how it works when we get there in a minute. So the second argument that you need to know is distance. Okay? Distance. Okay? How does distance affect my nucleus? Well, the further my electrons get away from the nucleus, what happens to the attractive forces? They dissipate, which just means it starts to what? Decrease. It starts to go away. Which means my distant electrons are held loosely, and that means they can be easily removed. So now what's happened to the energy it takes to remove them? It's gotten lower. We're going to relate this to energy whenever possible. Okay? Why has my distance increased as I go down the periodic table? Because this is what the argument you will use, number 2, we'll use that if we're going down the periodic table.
Is there radius increases?
The radius is increased, but why has the radius increased?
Because the up there.
Look, here I'm at 1s, then 3s, 4s, 5s, 6s, 7s. So every time I go down a period, I've added a whole nother what? Energy level. So I've added a whole nother energy shell, which means the size of my atom keeps getting what? Bigger and bigger and bigger, which means the distance my electrons from the nucleus keeps getting larger and larger and larger, which means the attractive force between those electrons and the nucleus is getting weaker and weaker.
So it's like Donald Trump building a wall.
He said he's gonna make Mexico before.
We see this? We understand this? Okay. All right. Number 3. Shielding. Shielding is one of those arguments that you can use it as long as you properly understand it and you know that the absolute only time that you can use this argument is if you're going up and down the periodic table. Shielding never, ever, 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 ever in 1,000 years works if you're going across the periodic table. Okay? And so shielding is one of those that, yes, you can use. And if you understand it, go for it. Write it. But don't make this one your go-to argument. Okay? Going down the periodic table, I want you to talk about adding energy levels and distance more than I want you to talk about shielding. Okay? What are we talking about when we talk about shielding? Okay? I've got the positive nucleus, right? And then I've got energy level 1 that's going to be relatively, these electrons are going to be close to the nucleus, right? Then I've got energy level 2. How many electrons can I fit in energy level 2?
No, 6. Wait.
2.
Don't go 2s2?
8. I can fit 8. Because in energy level 2, I've got 2s2, 2p6.
Oh, okay.
So that's a total of 8 electrons, right? So then I fit 1, 2, 3, 4, 5, 6, 7, 8. And all of these are negative. But then I notice when I get to the third energy level, all of a sudden, the distance between my radius, between my energy levels, has gotten a little bit bigger. Well, I drew it a lot bit bigger so you could tell the difference, but you get what I'm saying. It got bigger, okay? So why are these electrons pushed so far out? Because of electron shielding. These electrons in what we call the inner core, and the inner core, by the way, is just all of the electrons that are not in the outermost. Okay? So all of the electrons in the inner core are shielding these outside electrons from feeling any of the positive attractive force. Do we see that? So therefore, they're causing these electrons to be what? Repelled and pushed out. We see that? That's electron shielding.
Yeah,
Do we see why it only works as you go down the periodic table? Okay. Because as we go down, we add energy levels, which increases our electron shielding. Because the more electrons I put between the nucleus and the outer electrons, the less of that pull they're going to feel from the nucleus. We see that? We got that? Okay. And then energy level, and then reason number 4 is just something you always need to remember. We just talked about it. We're always trying to minimize the electron-electron repulsions, okay? Because we always want the atom to be in the lowest energy state possible to make it what? More stable.
I like 4.
All right. We feel good about this?
Yep.
All right, I'm going to call it a day here. And when you come in tomorrow, be prepared to finish out the rest of these notes.
We're
Okay.
taking this quiz tomorrow.
All right, and we're going to take a quiz tomorrow on electron configuration, orbital notation.